Hi everyone, let's continue. We're going to continue looking at scatter plots, linear relationships, and correlation or associations. Suppose Jake is driving towards Los Angeles at a constant rate of speed. After 3 hours, he notices that he is 172 miles away, and after 4 hours, he notices that he is 110 miles away. Part A asks you to write the information above as two ordered pairs, with time being the independent variable or first variable, and the distance from Los Angeles being the dependent variable or second variable. So what I like to do is I actually like to just label this and set up a coordinate as my x and y. So our first variable, our x, will be time. So I'm just going to call this will be Jake's drive time in hours. And this I'm going to call my second variable. This will be the distance from LA. And this will be in miles. And this will help when we get to parts C and D down below. So what's our first coordinate going to be? So, well, it says after 3 hours of driving, he is 172 miles away. And this says that after 4 hours, he is 110 miles away. So now we have our 2 points. Part B asks you to use the ordered pairs from Part A and write a linear equation that models the distance Jake is away from Los Angeles D as a function of the time he's been driving T. So, what do we need to start with? Well, just like before, 2 things we need when we're looking at a line, right? We need slope, and we also need a point. Well, we have 2 points. Remember, it doesn't matter which one we use, but we'll get to that later. Let's find the slope. Remember our slope, y2 minus y1 over x2 minus x1, or the difference in the y's over the difference in the x's, or change in y over change in x. Well, remember, if it helps, write this down. We can say that this will be our x1, y1, this will be our x2, y2. So our y2 minus y1, this will give us 110 miles on top minus 172 miles. And on the bottom, we're going to have 4 hours minus 3 hours. So we do those subtractions. This will give us negative 62 over 1. Or we can just say that this would be what? Negative 62. So we have our slope. And if we plug that into our y equals mx plus b, right now we're going to have y equals negative 62x plus b. And how do we find, well, what are we missing? Remember, we're missing the b. So how do we find the b? Well, that's what we're going to use the point for, right? We're going to use that point. Well, which one do we want to use? Doesn't matter which one. I'm going to use 4 and 110 just because 110 is smaller than 172. So doesn't matter which one. I am going to use the 4 and the 110. So if I plug this in for my x and y now, this tells me that when y is 110, x is 4. So we have 110 equals negative 62 times 4 plus our b. And now we just have to solve for b. So this will give us 110 equals negative 62 times 4. What's that going to give us? That'll give us, if it helps, remember, just go off to the side and calculate that out. 2 times 4 is 8. 4 times 6 is 24. So this will give us negative 248 plus b. And solving for b, let's move this over. And this will give us 358 equals b. And remember, well, that's what we were missing. So we plug that back into here, and what do we get? We get y equals negative 62x plus 358. And normally we just like to be done here, but remember, what's the question asking? We don't want to always use y and x. We want to get used to using other variables that have meaning. So what does it say? That, well, what's y, what's our x? Well, what does x represent? X is what? The time, right? And that's our t, so that would be our t here. And what's our y? Our y is the distance from Los Angeles, and that's our d. So let's substitute those in. So we have d equals negative 62 times t plus 358. I know we don't normally like using t's because they look like the plus signs, but just change it a little bit. It won't be too bad. All right. So now we have our equation. The distance that Jake is from LA equals negative 62 times the time he's been driving in hours plus 358. All right, let's move into part C. I'll leave a little space because I'm going to rewrite that equation above just so we have something to reference. So here we had d equals negative 62t plus 358. So part C asks you, what is the slope of your linear equation, including the units? So what's our slope from above? That's our m. Our m was negative 62. And remember that we have to include the units. This is very important. And remember, what was m? M was y2 minus y1, or we can say the change in y over the change in x. So, well, let's look at this a second and say, well, what would our units be? What were the units in the y variable? Well, this is where this comes in. Look above on part A. That's why I listed this out. Remember, it's y over x. So what is y? Y is in miles, and x is in hours. So what do we have? Miles over hours, which is miles per hour. So this would be miles per hour. Well, that's our slope with units. Now it asks us to what? Write a sentence to interpret the slope in context of the information. Before we actually write our sentence, I'm going to rewrite the slope. And this will really help with these interpretations. Remember, you can write any number over what? Over 1, right? So this would be negative 62 miles for every what? 1 hour. So what does this tell us? This tells us that for every 1 hour of time Jake drives, his distance from LA is decreasing by 62 miles on average. And that's exactly what we're going to write here. So we're going to say that for every 1 hour increase in time Jake drives, what happens? So for every 1 hour increase in time Jake drives, his distance, remember, not just distance, right? His distance, what? His distance from LA decreases by 62 miles. And I'm going to say on average here. The slope is also an average rate of change. So we just want to make sure that we put that in there, that we talk about that this is on average. This is how his distance from LA is changing for every 1 hour increase in time that he drives. Let's move on to part D. Part D asks you, what is the y-intercept of your linear equation? Write a sentence to interpret the y-intercept. So, well, this is our equation. We got our slope right here. This was our negative 62 miles per hour, which means that this would be our y-intercept. Well, when we're writing the y-intercept, it's important, it's helpful to actually write it as a coordinate. So how do we write the coordinate? Well, the y-intercept is, well, that's the y, the number is 358. So this would be 0 for the x, 358 for the y. And what does this mean? Remember, the x represents the time you spent driving, and the y represents this distance from LA. So this says that after 0 hours of Jake driving, he is what? He is 358 miles away from Los Angeles. So this is kind of his initial start time because he hasn't been driving, right? 0 hours drive time, which means that this is how far away he is when he started his trip. So let's say that. This says that after 0 hours of driving, Jake is predicted to be 358 miles away from Los Angeles, from LA. So remember, let's elaborate a little bit. So this would represent Jake's initial, or starting distance, if you want to say, or starting distance from LA. So those are two key points right here that we're looking at. We're looking at the slope and the y-intercept, and those are two key points. And remember, we want to make sure that we interpret each one of these in detail. Let's continue on to the next page. Let's look at the graph, or a graph. Scatter plots may be the most common and most effective display for data. Well, down here we have a scatter plot. Well, what can we see? In a scatter plot, we can see patterns, trends, or relationships, and even the occasional extraordinary value or values sitting apart from the others called, these would be our outliers. Okay. Scatter plots are one of the best ways to start observing the relationship, and the ideal way to picture associations between, well, these are still what? Quantitative values. So we're looking still at quantitative variables. Quantitative variables. So let's look at the scatter plot. Here we have a scatter plot. X would be a driver's age in years, and the Y is representing the max distance the driver can read a sign from in feet. So what do you think each dot represents here? Each dot represents a driver, right? Because that's what we're measuring here. We're looking at drivers and the maximum distance that they could read a sign. So when we're looking at a data set, well, this was given to us, but suppose we were just given a data set and we want to know, well, which one goes on the x and which one goes on the y-axis. Well, let's start, instead of talking about x and y, we're going to start talking about these variables in other ways. So the first thing we're going to talk about an explanatory variable. An explanatory variable explains or may influence changes in a response variable. And our explanatory variable is the x-coordinate. Well, what do you think our other variable is going to be called? It's right over here, right? Our next one will be the response. So a response variable measures an outcome of a study, and well, this is our y-coordinate. So I'd like you to start thinking about those variables in that terminology, to say explanatory and response instead of x and y. So we have explanatory and response instead of saying x and y. And well, we need to decide which one is the explanatory, which one is the response, and sometimes there is no distinction, so it doesn't matter which one we call which. So let's look at an example. Identify the explanatory and response variable in the following. How the price of a package of meat is related to the weight of a package. So here we're looking at two types of variables, right? Or two variables. We're looking at price and we're looking at weight. So which one do you think explains the other, or which one do you think is a response to the other? So, well, on our explanatory, well, we'll call this the weight, because we'd say what? The weight would what? Explain the price, or the price would be a response to the weight. Continue down, and this is going to lead us into the four things we're going to discuss when looking at a scatter plot. So the four things we're going to talk about direction, we're going to talk about form, strength, and outliers. These are kind of a snapshot of the four key things we're going to want to make sure to discuss when looking at a scatter plot. Okay, looking at direction, well, the direction could be positive, negative, or neither. So a positive relationship will, well, rise or fall to the right in a line. So if it's positive, that's going to go uphill, so that's going to rise. And a negative relationship is going to fall as you move from left to right. So suppose it's not a positive or negative, and we haven't got to strength yet, but if it's not positive or negative, can it still have a strong relationship? So can you think of a case or a picture of a graph that would be neither positive or negative, but would still have a strong relationship? Well, yes. So consider the height of a ball as it's thrown. The height of a ball as it is thrown. So if we think about this, right, then here we'd have time, here we would have height. So notice here, right, I'm picking my explanatory as time, the response is height, and, well, if you throw a ball, what's it look like? It would follow that kind of path, right? This kind of parabolic path. And, well, is this positive or negative? Well, no, because it goes up and then it goes down, right? So it's positive and negative, but you don't say both. So this wouldn't really have a direction, but does it have a strong relationship? Yes, it does, right? It's very strong on the pattern. So that's what we mean by that. And we'll get into these forms a little bit later. Moving down, talking about form. So when we talk about form, we're pretty much talking about the shape. And for us right now, we're looking at two forms. We're looking at linear forms, and we're going to look at nonlinear forms. Or you might hear it called curvilinear. So we'll have linear and curved, right? And sometimes it might not be either, and it might just be a jumble and not have any kind of form to it. So let's look at the first form, or the first one. This, what does this look like? If you're looking at this, this kind of looks like, what would you say? Linear or curvilinear or neither? This looks like it's following a general trend, right? It's following that path. And so this one I would say is linear. And what about the next one? This is what? Definitely we can see some kind of curve happening, right? So this is a curve. So we could just say that. We can say it's a curve or curvilinear if you want to. And how about this one? The third one. Now this one's a little bit tough because, well, let's look at this and say, well, I'm looking at a line, for instance. Does that line do pretty good of modeling it? I think so. I mean, it's following that kind of general path, but does a curve fit it also? And then you'd ask yourself, well, which one is better? Do you think the line fits better or the curve fits better? To me, if I look at this, this looks like it definitely has a curve to it, right? So I would say a curve fits better. And sometimes it's difficult to tell depending on what we're looking at, and we'll have ways to measure which one would actually be better to support that kind of conclusion. So on this one, I would say that a curve fits better, or curvilinear. Moving down to our next part, we're looking at strength. So what do you think? If you look at these two pictures, I think strength kind of makes sense, right? I mean, what do you think? This one is stronger than this one. Why? Because, well, the data is much more tightly packed, right? It's closer to the line than this one. This is spread out across the line. So they both have linear trends. It's just that this one is closer. And that's all we're going to say. The stronger the relationship, we can say the closer or more tightly packed and more tightly packed the data is to the line or curve, because we will look at curves too. So direction, form, strength, and our last one, outliers. Now we'll move on to the next page, just looking at that. And what is an outlier? Well, an outlier, remember, it's just that unusual point. So we can say that this is a point that deviates from the pattern of the relationship. A point that deviates or does not follow the path of the relationship. That deviates from the, let's say pattern, not path. The pattern of the relationship or association. Remember, outliers are not necessarily bad points, they're just unusual, right? So let's put all this together. So direction, form, strength, outliers, and we're going to tie this into writing a summary analysis paragraph. So back to our example that we've already looked at, we have a summary analysis paragraph. The following scatter plot describes the association between a driver's age in years and the maximum distance the driver can read a sign from in feet. Write a summary analysis paragraph on the given data. Be sure to include the direction, form, strength, and outliers, and what does the data suggest. So here we have the driver's age in years, our x or explanatory variable, and our response or y variable is the maximum distance to read a sign in feet. And, well, what can we say about this? Remember, if it helps, pause the video and think about it for a minute, and then let's continue. So if we're looking at this, what's the direction appear to be? It looks like it's going down, so we can say that the direction would be negative. Does it appear linear, curvilinear? This looks like it follows a pretty decent line, right? It's going down in a line. That's direction, that's form. What about the strength? Would you say that this is a strong relationship, moderately strong, weak? So this is just kind of a visual inspection and use your best judgment. Well, I would look at that and I'd probably say that's moderately strong. It's not really, really tight. It could be spread out a little bit more to be weaker, but to me it looks like it's moderately strong. And do there appear to be any outliers? I don't think there are any outliers. It doesn't appear to be any because everything's just following that general path. And those are the things that you want to write about. So remember, when we're writing our summary analysis, it's important to start with an introduction sentence. So you want to have an intro, tell the reader what they're looking at, address the 4 parts, the direction, the form, the strength, and the outliers, and make sure to write about, well, what does the data suggest? The data suggests that, what is this telling you? As a driver's age, increases, what's happening to the maximum distance that the driver could read a sign from? It's going down, right? So this says that, and that's what it's saying. So I want you to pause the video a minute, write a little summary analysis, and then compare it to the one I put up. So pause the video and write one. All right? So I wrote a brief little paragraph down here. The scatter plot above describes the relationship between a driver's age in years and the maximum distance the driver can read a sign from in feet. The direction of the association is negative and linear in form with moderate strength. There does not appear to be any outliers in this data set. And the data is suggesting that as the age of a driver increases, the maximum distance the driver can read a sign from decreases. Okay, so if you need to write this down still, pause the video and continue writing, and I'll see you on the next video.